on systems of inequalities and linear programming. There's a lot of mathematical descriptions of real situations that we can best describe using inequalities rather than equations. A couple of examples: using a machine for no more than 12 hours a day, producing at least 500 cases. Both of these are inequalities. No more than means that many or less, so less than or equal to 12. At least means that many or more, so greater than or equal to 500. Now, in order to do the systems of inequalities and the linear programming, first we need to review how to graph an inequality, a linear inequality. And the first thing that you do when you graph a linear inequality is you draw a line. And you'll notice that this line divides the plane into three sets of points. You have the points that are actually on the line. You have the points that are on the half of the graph designated by the P here with the light blue shading. And then the other half of the points are in the region labeled Q with the darker blue shading. So we have three regions. The dividing line is one, and then each half is another region. A linear inequality in two variables has this form: ax plus by is less than or equal to c, or it might be greater than or equal to c. A, B, and C are real numbers. A and B are not both equal to 0, and the symbol could be greater than or equal to, or less than, or greater than. Now, the graph of a linear inequality is a half plane. So when we have ax plus by less than or equal to c, that is going to be a half plane. Remember just a minute ago we talked about how the line divides the plane into two halves. The line itself is a region, and then each half is a region. So one of those two regions is going to solve the linear inequality. It's going to contain all of the solutions to the linear inequality. So for example, let's say we want to graph 3x minus 2y is less than or equal to 6. The first thing we do is we graph the line. 3x minus 2y equals 6. Now what we need to do is we need to figure out which side of the line contains the points that will be solutions for this problem, because all of the points will lie on one side or the other of this line. Now there's a lot of different methods of doing it. One of the easiest is to pick a point that is not on the line, for example 0, 0, and put that in for x and y, and then see if it makes it true. If it makes the inequality true, then the side that that point is on will be shaded. If it does not make it true, then the opposite side of the line will be shaded. So if you put in 0, 0, we get 0 minus 0 is less than or equal to 6. This is true, so we will shade the side of the line that contains the point 0, 0. And that's the solution to our linear inequality. Greater than 4. Pause the recording, give it a try, and resume to check your answer. The boundary line is the line x plus 4y equals 4. And since the point on those lines don't satisfy the inequality, in other words, this is a greater than, not a greater than or equal to, we're going to draw the line in dashed. If it had been an equal to, we would have made a solid line. And there's another way you could see here that you can determine which side is shaded. Again, one way you can do it is you can pick a point like 0, 0. If you put 0, 0 in, you get that 0 is greater than 4, which is not true, which means that side will not be shaded and the other side will be. Another way to do it is to solve the inequality for y. When you get y by itself on the left, then if its y is greater than, then the region above the line will be shaded, and if it's less than, the region below the line will be shaded. The only thing I would caution you with is that if you need to multiply or divide by a negative in order to get y by itself, you need to remember the rule that when you multiply both sides of an inequality by a negative or divide by a negative, that you need to flip the inequality symbol around. Now, we didn't have to do that here. It's just a word of caution for future problems. Okay, so graphing an inequality. 1, for a function f, the graph y is less than f of x contains all points that are below the graph y equals f of x. This is what I just mentioned below if you, on the previous slide. If you solve the inequality for y, then you can kind of go by the inequality symbol. If it's a less than, it'll shade below. If it's a greater than, it'll be above that line. We also have this point, if the inequality is not or cannot be solved for y, then you should choose a test point not on the boundary. If it satisfies the inequality, the graph includes all the points on the same side as the test point. Otherwise, it's all the points on the other side. So this is just summarizing the two methods for determining which side should be shaded. Now we're going to solve a system of inequalities. And a system of inequalities, like a system of equations, is a group of two or more inequalities that you are going to graph at the same time. And the answer is going to be the overlap of the shadings. So try this example. You're going to graph x is greater than 6 minus 2y, and x squared is less than 2y. And then you're going to shade those, and the overlap will be your solution. Pause the recording, give this a try, and resume to check your answer. You can do these on your graphing calculator. You do need to solve for y if you're going to do that. So we have y1 is 6 minus x over 2, and y2 is x squared over 2. On your calculator too, if you move, when you put these into y1 and y2, if you move the cursor all the way over to the left of the y1 and y2, you can hit enter and change the symbols there. The symbols that you see here on the screenshot indicate that you want the graph shaded above the line or above the curve, and that's what happens on your graph. There's one that points down to the left, and that would indicate that you want the graph to be shaded below the curve. So this is a way you can actually use your calculator to help you with the shadings. The answers where you see the overlap, the calculator will alternate shading styles. You'll notice one graph is shaded with vertical lines, the other with horizontal, and you can easily tell where they meet. Keep in mind that you do need to understand which side needs to be shaded because you need to tell the graph what to do. You also need to understand that the graph is not going to put these in as dashed or solid lines. So you do need to remember when you draw this that both curves, both the line and the curve, are going to be dashed lines because both symbols were greater than, less than. They did not have the equal line underneath. X equals 6 minus 2y, and we discovered that we need to shade that above it. Then you graph the parabola, and notice both of these are dashed, and then when you put them together, the overlap, the purple region, is the solution. I'm going to slide into something called linear programming, and this may seem like a change of subjects, but it's really not, because the whole reason we talked about linear inequalities is that we are going to use those to do the linear programming. So an important application of mathematics to business and social science is called linear programming. It's used to find an optimum value, a maximum or a minimum. We want to minimize the cost of production of something. We want to maximize the profit on the sale of something, and that's what it's used for. It was first developed to solve problems in allocating supplies for the Air Force during World War II. So it's been around for a while. And we'll kind of walk through this. A company makes two products, MP3 players and Blu-ray players. Each MP3 player gives a profit of $30, while each Blu-ray player produces $70. The company must manufacture at least 10 MP3 players per day to satisfy one of its customers, but no more than 50 because of production restrictions. The number of Blu-ray players produced cannot exceed 60 per day, and the number of MP3 players cannot exceed the number of Blu-ray players. How many of each should the company manufacture to obtain a maximum profit? Okay, so the first thing we have to do is kind of plow our way through all these words and come up with some equations. And the first thing we're going to do is define our variables. So X is going to be the number of MP3 players to be produced daily. We know that they have to produce, let's see, at least 10, but no more than 50. So we're going to be writing that in a minute. And we're going to let Y be the number of Blu-ray players that are produced every day. And we know that they cannot exceed 60, so it needs to be less than or equal to 60 and 50. That means X is greater than or equal to 10, and it's also less than or equal to 50. We also know that no more than 60 Blu-ray players can be made in one day, so Y is less than or equal to 60. We also know that MP3 players, the number produced, cannot go above the number of Blu-ray players. So we also know that X has to be less than or equal to Y. Something else that we know from this is that the number of MP3 players and Blu-ray players cannot be negative. Now that's just a common sense thing. You can't produce a negative number of items. So we know that X and Y have to both be greater than 0. These are all called constraints. Okay, by constraints we mean they're limitations on what X and Y can be. So our constraints are X is greater than or equal to 10, but less than or equal to 50. Y is less than or equal to 60. X is less than or equal to Y, and then both of them are greater than or equal to 0. What we're going to do first is we're going to graph the constraints. Now we haven't even brought the money into it yet. First thing we're going to do is graph all of these constraints, all these things that are restricting the production. And then we need to find the intersection of the feasible values of X and Y. They must satisfy all constraints. Then we'll maximize the profit. So what we're going to do is we're going to graph all of these inequalities. We're going to find the intersection, the place where all of them overlap. This place is called the feasible region. Once we get that, we're going to maximize the profit. And the profit is 30X plus 70Y because you're selling the MP3 players for 30 and the Blu-ray for 70. The area just said enclosed by the constraints is called the region of feasible solutions or feasible region. Okay, this is where everything overlaps. When we graph everything, it has to be in the first quadrant. And then we graph the diagonal line is the line X equals Y. And then we also have the X has to be between 10 and 50. And we put those together and we get a polygon. In fact, if you remember from geometry, this is a trapezoid. And this is the region where our solutions have to come from. Anything outside of this is not feasible because it does not meet the conditions we need for production. The profit is a line, it's 3X plus 70Y, and we want to make it as large as possible. Now, all of the possible lines that we could draw, I mean, we could put in any number we want to. And we've put in multiple numbers here for profit. We've got 7,000, 3,000, 1,000, even 0. And one thing you notice about all these lines is that the slopes are all the same. They're all parallel to each other. So the line that we're trying to maximize, all the possible lines are parallel to each other. And but we're only considering the lines, we can only consider the lines that go through our feasible region. So they have to go through that trapezoid we colored in. And notice that the maximum and minimum values for profit occur when the line intersects a corner of the region. So it's got to at least touch the region. We can't consider any lines outside of it. And if you keep drawing these lines, what you'll notice is you're going to find the maximum profit occurs when it touches one of the corners, and the same will be true for minimum. Now, we're not interested in minimum right now, but the same would be true for minimum. That means that when we want to find a maximum or minimum, what we need to do is test the points that represent the corners of this region. We're going to test them in our profit function or in our objective function, and we're going to see which point gives us a maximum, if that's what we're looking for, or a minimum. Like in the left column, I've listed the corner points. In the middle, I've put each corner point in for X and Y in our equation. And in the right, I've listed, well, what you get when you solve those. And you'll notice that we have a maximum profit of $5,700 when you are making 50 MP3 players and 60 Blu-ray players. It occurs at a vertex of the region of feasible solutions. In English, you graph all of those inequalities, all of those constraints. It forms a geometric shape. Your solution, if there is one, will occur at one of the corners of that shape that you created by overlapping your inequalities. Steps. Step 1, write the objective function and all the constraints. Step 2, graph the constraints. Those are going to be the inequalities. Graph those first and get that region where they overlap. Step 3, identify all vertices or corner points, and you may need to find where the different lines intersect to do that. Step 4, find the value of the objective function at each vertex. Do the chart like I just showed you. And then step 5, the solution is given by the vertex producing the optimum value. It could be a maximum or a minimum of the objective function. Now let's try one. Robin gives her dog Susie vitamin supplements every day. She wants at least 16 units of K, at least 5 units of vitamin B, B1, and at least 20 units of riboflavin. She can choose between brand X pills costing 10 cents each that contain 8 units of K, 1 of B, and 2 of riboflavin, and brand Y costing 20 cents each that contain 2 units of K1, 1 of B1, and 7 of riboflavin. How many of each pill should she buy to minimize her costs and yet fulfill her daily requirements? All right, so again, we need to pick a variable. We've got 2 things we're talking about here, 2 different pills, brand X and brand Y. So let's conveniently name them X for brand X and Y for brand Y. And our objective function is going to be our cost, which is going to be 10 cents times X, so 0.1X, times 0.2Y. Or you can actually just use 10X plus 2Y, or 20Y, sorry, 10X plus 20Y, either way. Okay, so we've defined our variables and we've got our objective function. Now what we need to do is we need to create some inequalities based on what she wants. So, and we get 8 of them from X and 2 of them from Y. So 8 from brand X and 2 from brand Y have to be greater than or equal to 16. Now vitamin B1, she needs at least 5, so greater than or equal to 5. She gets 1 from brand X and exactly 1 from brand Y, so X plus Y equals 5, or is greater than or equal to 5 rather. And then at least 20 of riboflavin. Well, she only gets 2 of those out of brand X and 7 from brand Y, so 2x plus 7y is greater than or equal to 20. And we also know that she can't give a negative amount of pills, so they both need to be greater than or equal to 0. Doesn't enclose a region. In fact, it's kind of just keeps going. But actually that's okay because we're not trying to find a maximum, so we don't need to worry about the upper areas there. We're trying to find a minimum. And we have 4 corners here. We have 0, 8, 1, 4, 3, 2, and 10, 0. So we're going to put all of those into our chart, and we're going to put them each into our objective function. And you can see that we get 100, 70, 90, and 160. She gets a minimum cost of 70 cents per day when she gives 3 pills of brand X and 2 of brand Y. Pause the recording, give these a try, and resume to check your answer. Continue this way through the rest of the recording.